Welcome back, everybody. So first, I have to say, don't worry, there's only a few more slides. We are almost done with that scary part of the course with so much theory. I just wanted to go back to that slide because there was a few questions during the break on what, why we are doing that, and so on. I told you about the fun fact that a table with two attributes is in the Boyce code normal form. And I also told you that the goal is to decompose tables into tables that are all in the Boyce code normal form. And this is why you might think of the naive idea, let's just decompose it in table with two attributes and we are done, right? Because two attributes, they will be in DCNF. But I wanted to show you why that doesn't work, because I told you we would project. So this is the projection. We project it, we project it, we project it. But then when we join them back, we get this, right? This here, what you see now, is the join of the three tables. Who agrees it's not the same? Right? It's not the same. So this is why we are saying it's bigger. You know, it's always going to be bigger when it doesn't work. So we get back something that has tuples that shouldn't be there, right? These tuples have nothing to do here. For example, I have A1 foo true, A1 bar false, but now I have A1 foo false that now appeared out of nowhere. And now I have A1 bar true that appeared out of nowhere. So these two tuples right here, they shouldn't be in there. So it means that when we try to decompose it in this way, we introduce these ghost tuples that have nothing to do in here, but because of the join, now they are here, right? So this is why you can't do that, right? You cannot just decompose randomly. Instead, you have to decompose by finding a functional dependency that breaks BCNF, and you get your decomposition that way. The first table will be basically the transitive closure of the left-hand side that's not a super key. And the other table will be the left-hand side plus the rest. That's basically how you do it well. And then you iterate if it's still not enough. So now I was telling you about the fact that the join needs to give you back the original table without additional tuples. I told you that in one direction, it's very easy. It can never be smaller. You can never get a join that gets you something smaller. It can only be bigger. So we need to do the other way around. Can we exclude that it's bigger? So basically, we have this tuple in the join. And I'm asking, is it a ghost tuple that appeared out of nowhere, this tuple in the join, or was it really in the original table, right? And so what we do is we say, okay, if it was in the join, then it must have originated from here and here, right? And I can even show you on the original slide the same thing of what we mean, just so that it's a bit less abstract. If I have this tuple right here in the join, it must come from somewhere. Well, it comes from A1, it came from A foo, and it came from A false, right? From here. So if you have it in the join, it must have been, the projections must have been in the original tables. Who is with me, right? And now we just must ask, then was it in here, right? And so this is where the Chase algorithm is going to tell us whether it can be a ghost tuple or whether it's really an original tuple that should be here. So basically what we said is that since these are in the decomposed tables, they must have been projected from somewhere in the original table. So AD must have come from some tuple that had AD and whatever in here. ABC must have come from some tuple ABC and then whatever in here. So instead of just saying whatever, I'm just going to give them names, right? So I'm going to call B1 whatever was in here, C1 whatever was in here, and D2 whatever was in here, right? I'm just giving names to the values we don't know. So at that point, what I'm saying is that if I had ABCD in the join, that may or may not be a ghost, there must have been two tuples in the original table of the form AB1C1D, ABCD2, where ABCD are the ones from my tuple in the join. Small note, I don't know if these tuples could not be the same, right? Maybe it's the same tuple, right? But there has to be two tuples that look like that, who may or may not be the same tuple. And I left you during the break at, we have a functional dependency in here. So what can you say about these values? Can you actually tell me what some of them are? B1, C1, or D2 maybe? Can you tell me? So as a reminder, the functional dependency that we had in that case was that A determines D. So if A determines D, what can you tell me? Some equality between values. A determines D. Yes? Exactly. D has to be equal to D2. Because if I have the functional dependency that A determines D, it means that D is a function of A. But now I see twice A here. It's the same value. So if I have the same value here, I must necessarily also have the same value there because of this. Who agrees? Right? So we know that D2 must be D. Right? D2 must be equal to D. Otherwise, the functional dependency wouldn't hold. And again, the reason I'm saying that is that we are here in the original table. That's the original table that has this functional dependency. So then I can remove the 2 here and say it's D. Now, do you see what's just happening here in front of your eyes? Do you see that? It means ABCD was necessarily in the original table. Do you see that? Do you agree with that? Right? So it means that it was not a ghost. Right? I've just proven that I picked a tuple in the join, and I showed it wasn't a ghost. And in order to show that it wasn't a ghost, I used the functional dependency that applies. And because of that functional dependency, I was able to show that. And the reason that worked is because I was careful using a decomposition based on a functional dependency. That's the reason it's working. If you try to do the same thing, you try to do the chase algorithm with this one. So if you try to do the chase algorithm with this one, and you would have potentially this tuple, you would be able to project it like to here, but then you would be stuck because you wouldn't have a functional dependency to apply. You wouldn't be able to prove that it was in the original table. And of course, you wouldn't be able to prove it because it was not in the original table, right? But this is because the way we decompose here was nonsense. Here we just decomposed with just taking random subsets of attributes 2 by 2 by 2, right? So again, what I'm telling you is that the chase algorithm is, it's a little bit like a bingo game, right? That you just say bingo whenever you have it, right? And it always works if you apply it on a decomposition that was carefully obtained with a functional dependency that breaks BCNF, right? And otherwise, maybe it's not going to work. All right, who is with me? Very good. So now you can play. It's actually pretty common in textbooks and at exams to apply the chase algorithm, pretty popular in computer science. It feels great because that's really a bingo game. That's really what it really is. Okay. So where are we here? I'm about to conclude database design theory. We basically were able to decompose a relational table that might be too big, relational table with plenty of anomalies and doing too many things. We decomposed it into smaller tables by projecting on various subsets of attributes in such a way that all the tables in the decomposition are in the Boyce code normal form, BCNF, right? So they're all in the Boyce code normal form. We just kept iterating and decomposing further until we get table in BCNF. It will necessarily succeed at some point because when you arrive at just 2 attributes, then that's it, right? It cannot be that you decompose and then you're not in BCNF because eventually you will arrive at 2 attributes in the worst case. So all the relational tables are in BCNF, and it is a lossless join. What I mean here is just what I've already told you. It's the idea that when you join them back, you get back the original table. Lossless join means there's no ghost tuples, right? And here, the fact that we didn't lose anything can seem at first surprising because it's not like we lose tuples. On the contrary, we get ghost tuples. So why am I saying we don't lose anything when in fact we get ghost tuples? Well, do you agree that if I take an Excel spreadsheet on your laptop and I add 1 million more row combinations and so on, do you agree you've lost your data? Right? If I inundate your spreadsheet with plenty of meaningless lines of text, it's the same as saying that you lost your data. Right? Is that intuitive? Right? Lossless means the tuples must exactly be the same. right? When you join back the decomposed tables, you get back the original table. It might, however, happen that it doesn't preserve all dependencies. It might be that you had functional dependencies in the original table that get lost in the process, and we have to live with that, right? So in our case, we might have the Boyce code normal form. So we avoided anomalies with the Boyce code normal form. It's really popular to avoid anomalies. We succeeded with the bingo game. So it's always lossless. The join of the tables always give you back the original table, but you might lose dependencies in the process. Just to say a few more words on that, just a concrete example. Imagine that I decompose in this way. And now imagine that I have a functional dependency that says B determines D, another one, right? B determines D. Do you agree this one is lost now? Because B and D are not together here, and B and D are not together there, right? So I might have a few functional dependencies that I just lose, right? Okay. So it's an impossibility triangle. There's other normal forms. There's cases where you might not be lossless. So that's the ghost stoppers that I told you about. So here you wouldn't lose anything, but the join is not perfect. And finally, you can actually be lossless and preserve the dependencies, but then you might not avoid all anomalies, right? So that's basically, it's difficult to have everything at the same time. Okay, so just to tell you that it's a bit difficult to basically, you will not get a perfect set of tables. All right. Any questions so far? Who is with me? Right, very good. So now I have a few more slides, but this is extra, this is bonus. You don't have to worry too much. I just want to show you the other normal forms very briefly. The only normal forms that we saw in this course are the first normal form and the Boyce code normal form. These are the two, right? First normal form, all flat. You don't have a table in a table in a table. Boyce code normal form, all the left-hand sides of non-trivial functional dependencies must be superkeys. These are the only two you're supposed to know. But just as a bonus and to show you, even though it's not exam material, there's more. Because in fact, as you can imagine, there is a second, there is a third, there is a fourth, there is a fifth, there is a sixth normal form. In fact, the Boyce code normal form is also known as the 3.5th normal form, because it's somewhere in between the third and the fourth. So, yeah.
What exactly more anomalies avoided mean?
More anomalies. So when I talk about anomalies, I mean you have a table that is too large, and when you try to delete data or to insert data or to update data, you run into problems. For example, in the table that I gave you as an example 2 weeks ago, you had the prices of the products. And it might be that when you try to update a price, if you don't update it everywhere, then you have inconsistencies. That is an anomaly. Or it could be that you try to delete a product, but then the customer that was the only customer that ordered it goes away with it. That is a delete anomaly, right? And so the goal of the database design theory is to avoid those anomalies. And basically the idea is that every normal form avoids more and more and more and more anomalies, right? So the higher the normal form, the better it gets at removing anomalies. And so the two normal forms remove some of them, the third normal form even more, the Boyce code normal form even more, then the fourth one even more, the fifth one even more, and so on. That's the idea. So that's what I was saying, is that the 3.5 is not perfect. It goes further than that. Does it make sense?
Is it the same as having BCNF? Question mark.
Oh, no, because you can also continue to avoid even more anomalies with the fourth and with the fifth normal form. I think, if I'm correct, that there is a general agreement that the fifth normal form pretty much eliminates all anomalies you want to eliminate. So the ultimate one is the fifth normal form. So this is why I said avoids more anomalies here. You know, it's like an advertisement where you don't want to, you know, so it doesn't avoid all of them, but more of them, right? So this is what I meant. Okay. Does it make sense? Right. But the fifth normal form is not part of the material, and neither is the second, neither in the third. The only ones are first and Boyce code, that's all. But still, I wanted to show you. how they relate. Because the Boyce code means that an attribute cannot depend on anything that's not a super key, right? It's just another way of saying that the left-hand side must be super keys. Well, in fact, the second and third are a bit more lenient. So the second and third normal form, they don't say that any attributes, they only look at the non-prime attributes. So basically, if you would have an attribute that is prime, meaning that it exists in one candidate key, then you close your eyes. You say, okay, it's prime, so I don't care if I have a functional dependency that's not a super key on the left, right? So they're a bit more lenient and only look at non-prime attributes like quantities, prices, that kind of things on the right-hand side. And then the difference between the second and the third is that when you look at the second normal form, it doesn't forbid anything that's not a super key. It only forbids it when it's a subset of a candidate key. You basically have a candidate key and something depends partly on it, right? Imagine that you have a super key that's made of a canton and a number to identify a car. So you have the canton and the number, but you might have things in your table that only depends on the canton, right? Like the capital city of the canton, for example. Then you have something that depends partially on a key, only on subset of a key and not the whole key. So this is what the second normal form gives you. And so in the third one, we say not just a subset, anything that's not a super key. There's other ways not to be a super key than to be a subset. And so this is the idea, right? Every time you get stricter and stricter and stricter. And so this is why there is this way of saying about normal forms, the key, the whole key, because you forget the subset, and nothing but the key, like this. And then they add, so help us code, Edgar code, of course, as a joke, right? So the key, the whole key, and nothing but the key. Okay, so these are the first normal forms. Again, not exam material. I'm just showing to you they exist, they are there, and there is some sort of hierarchy. What about 4, 5, and 6? And again, that's not exam material. The idea of the fourth normal form is that you have some key in there, some candidate key, let's say A, and B and C are kind of arbitrarily combined, right? They exist independently of each other. In other words, you have the whole combination, AX, AY, BX, BY, and so on. Here you might have AX, AZ, BX, BZ. It would be a Boyce code normal form, right? Here you will not find any functional dependency whose left-hand side would not be a super key. So it is in the Boyce code normal form. But do you see that you could still decompose it in this way? Do you agree these two tables joins back to that table? Do you agree? Who sees that? Right? It is the join. And so basically, we say that it's called the join dependency, basically, when you have that. We say that because we can decompose that table in this way, then we should. That's the idea of normal forms. And so the fourth normal form forces you to further decompose. And the fifth one is the ultimate one that basically forces you to decompose in this way. It's called the join dependency. They join back into the original table. What the fifth normal form says is all of your tables here, they must all be super keys. More precisely, the attributes of your projected tables must be super keys in the original one. Right. Again, not exam material, no need to remember, I'm just showing to you. And so the fifth one is considered the ultimate normal form in terms of anomalies. But you get the idea. Intuitively, what we're saying is that normal forms are about dejoining. We try to decompose the tables as much as we can in such a way that if we join them back, we get the original table. So the goal is to decompose. Whenever we see it's possible to obtain it as a join of smaller tables, then we go ahead and do it, right? That's the idea of the normal forms. Okay? And that's it. And again, I insist, not exam material, not exam material, not exam material, right? Only the first normal form, the Boyce code normal form, the Chase algorithm, this is exam material, but not the other one. I just wanted to show them to you quickly. By the way, there is a sixth normal form. I will show that to you in a couple of weeks, but this one is easy. It's when we have data cubes, actually, the sixth normal form. Everybody with me? Okay, so I'll take time for questions if there's any, a few minutes, and otherwise I'll move on to the next part, which should be a bit easier again. Any questions on Zoom?
Nothing.
Nothing? Right. Okay. It's what we are always told when you teach a lecture and you ask if there's questions, you should always give time, because if you say, are there questions? And then 5 minutes later, 5 seconds later, you already continued and nobody gets a chance to raise their hands. This is why I give a bit of time. But it seems that no question arises on Zoom. No question in the room. Okay. And I'll see you on the other side with